Okay, welcome to the 2016 Rossi Prize lecture. My name is Chris Reynolds. I'm chair of the High Energy Astrophysics Division of the AAS. And the Rossi Prize, the Bruno Rossi Prize, is the senior prize that we give from our division to honour a significant contribution to high energy astrophysics, with a particular emphasis on original and recent work. So it's awarded once per year, and we always have the successful winner give a presentation at the winter meeting. So the 2016 Bruno Rossi Prize is awarded to Professor Niel Brandt from the Pennsylvania State University, who led the effort to obtain the deepest Chandra fields, enabling the most sensitive cosmological X-ray surveys to date, and his work traces the accretion history of supermassive black holes and their coevolution with host galaxies across cosmic time. It's a great personal pleasure to be giving this award to Niel. I've known Niel for as long as I've been an astronomer. We were graduate students in Cambridge together a few years ago. So it's a personal pleasure to give this award to Niel. So congratulations, Niel. And there's a check of undisclosed amount here too. So without further ado, let me hand over the floor to Niel to give his talk on a good hard look at cosmic supermassive black hole growth.
Well, again, thank you very much for the award and for having me here. So today I'd like to tell you about work that we've been doing over the past about 17 years with cosmic X-ray surveys. We've been fortunate in high energy astrophysics in recent years to have a number of missions that are extremely powerful at cosmic X-ray surveys. We have, of course, the Chandra X-ray Observatory, the Xray multi-mirror mission Newton, and NuSTAR has at least 3 of them, and there are others as well. And my talk today, given the nature of the award, is going to focus on work largely with the Chandra X-ray Observatory, although I will bring in XMMNewton and NuSTAR as much as time allows as well. Before I go further, I want to stress that this is the work of many people. The success of the Chandra Deep Fields has relied on many people. Many students in my group, for example, have done heroic work on this over the years and continuing up to the present day. And equally heroic have been the many postdoctoral researchers that have come through my group over the years. And to all these people, I am very grateful for all of their efforts. And it's wonderful to see all these people going off, both the students and the postdocs, to have great new adventures and great careers, often around the world. And so it's been a pleasure to work with all of them. I also want to thank my collaborators worldwide. In my case, I'm especially personally grateful to the members of the Chandra Advanced CCD Imaging Spectrometer team at Penn State and beyond. These are some early pictures from the Chandra ACES team, headed by Professor Gordon Garmeyer, who is now a professor emeritus at Penn State. And this is a picture of Chandra ACES. It's a CCD-based X-ray detector. It's truly a wonderful instrument. It not only performs imaging, it is truly an imaging spectrometer. So at the same time you're performing X-ray imaging, you're measuring the photon energies for all the X-rays, so you get spectral information as well as variability information. And I have many other great collaborators listed here, for example, on these catalog paper author lists. And so this has been a big team effort. So what I'd like to do today is, first of all, tell you a little bit about the general utility of X-ray surveys of active galactic nuclei, why they're worthwhile doing. I'd then like to tell you about the Chandra Deep Fields specifically and what how they've been observed and what their basic nature is. I'd like to also tell you about then some selected first science results from the deepest X-ray survey so far, the 7 million second observation of the Chandra Deep Field-South, and I'll end with some future prospects. So I will move to this. So the X-ray emission that we observe from active galactic nuclei is thought to be produced in a coronal structure up above the accretion disk as pictured here. This is a coronal structure perhaps somewhat like the solar corona, but far more extreme. Instead of having temperatures of order 1,000,000 Kelvin, this has temperatures of order 1,000,000,000 Kelvin. And we observe the X-ray emission from active galactic nuclei to be nearly universal. So this coronal structure is almost always there in this very central regions close to the supermassive black hole. And there are various physical processes, interesting, operating in these corona. Compton upscattering of photons from the disk produces a lot of the X-rays that we observe. You can also have X-rays shining back down upon the disk or upon any other nuclear material, radiating it, interacting with it, and producing other X-ray signatures via the process called Compton reflection. And this is here, of course, is a UV to X-ray image. If you just make a sort of an X-ray based image, the contrast of the coronal loops relative to the disk is much more dramatic, okay? And you get this broadband X-ray spectrum as shown here being produced. You see that power law component running across the spectrum. That is thought to be associated with this Compton upscattering process. You get iron K-alpha line emission when via fluorescence processes, when the X-rays shine upon the disk and other material, you get a high-energy Compton reflection hump as well. Now, of course, this entire system that I've been talking about is buried down in the center of a galaxy. And so the X-rays and all the other AGN's emission that is produced has to get out of that system. And we know that the majority of active galaxies in the universe are obscured. There's a lot of material down in the nuclear regions, as well as more broadly throughout the galaxy, that can absorb X-rays or absorb other forms of radiation even more so and prevent them from getting out. But the X-rays have a big advantage in this respect, and that X-ray emission, particularly as you go to higher X-ray energies, is penetrating. You have reduced absorption bias, and that's what you're seeing here with this little movie. I'm adding absorption to that spectrum I just showed you in the previous overhead with a given amount of column density as labeled there. And to sort of give you some context there, the column density through your hand is of order 10 to the 23. The column density through your chest is of order 10 to the 24. Okay, and the absorption bias, another great thing about the penetrating nature of X-rays in this regard is the absorption bias actually drops as you go to high redshifts in these surveys because you gain access to increasingly penetrating rest frame X-ray emission. They can penetrate through very large columns. You can see the high energy emission there is not so affected even by very large column densities, and of course that's why X-rays are used for medical applications here on Earth. In addition to that penetrating aspect of X-rays also have low dilution by host galaxy starlight, and you can see that here in this optical image compared with an X-ray image. All the starlight is dropping out. You're just seeing the black hole related light in the center of this galaxy. So it gives you a very high contrast between starlight and black hole related light, letting you home in on where the accreting supermassive black holes are. And so X-rays, again, are maximizing that necessary contrast. Now, best of all, of course, is to combine the X-ray-based selection approaches with multi-wavelength-based approaches, and I'll be talking about that later on. Now, I want to say a few words about these X-ray surveys. This is a schematic from a review paper I did a lot of work on with Dave Alexander, showing the flux limit versus the solid angle coverage of various X-ray surveys. And as you can see, with X-ray observatories, including Chandra and XMMNewton and Rosita and earlier missions, Einstein Observatory is also shown here, a lot of really excellent X-ray surveys have been done. And they all together are necessary to give us our full comprehensive understanding of black hole growth throughout the universe, especially in obscured systems. I want to just show you a couple of examples of these surveys. Here, for example, is a really beautiful survey. This is the XMMNewton XXL-South field. This is a quite wide field survey. It's 25 square degrees, relatively shallow coverage, 10 kilosecond exposures, and for comparison, you can see the full moon there. There's about 10,000 sources detected in this particular survey. It detects the rare luminous sources, but it's not going sufficiently deep to get most of cosmic accretion power. Here's another great survey. This is the Chandra Cosmos field. This has been another extremely successful survey. This one attempts to get a good balance between getting a lot of cosmic accretion power, most, and also getting enough solid angle to give you large numbers of sources and being able to study cosmic structures. So this has been another example of a very successful survey. And again, from that plot, you can see there are many more. But today I'm going to be focusing, of course, on the very deep surveys. This is about the Chandra Deep Fields. So the Chandra Deep Fields are my personal favorites. They are sort of the ultimate in narrow field, ultra deep, pencil beam type X-ray surveys. Here they are. The Chandra Deep Field North there is shown on the left. The Chandra Deep Field-South is there on the right. These are very large investments of time with the Chandra X-ray Observatory, a 2 million second observation for the Deep Field North and a 7 million second observation for the Deep Field South. And these have been gathered over long periods of time, many years, as labeled there. And this lets us study variability of the X-ray sources over long time scales. And each of these fields, to give you a sense of context, covers about 2/3 the size of the full moon on the sky, okay? And in those sky regions, as you can see, we're detecting large numbers of sources, something like 755 in the Deep Field North, somewhat more than 1,000 now in the Deep Field South. And the most of these are indeed accreting supermassive black holes, active galactic nuclei, about 87% of them in the north and something like 71% of them in the south, according to our characterizations, which I'll tell you about in a minute. Now, in addition, as I said, to getting just imaging information, we have X-ray spectral and variability information for all these sources. So I can go and cut out any one of those sources and get an X-ray spectrum for it and characterize it spectrally and learn about its physical properties. That's another point I want to stress. So X-ray observations have this unique imaging plus spectral characteristic all at once, which is extremely powerful. Furthermore, I just want to highlight this aspect. Now in the very deepest observations, in the very center of the Deep Field South, which is that boxed region, which I'm showing here zoomed in. You can see the large numbers of sources there, color-coded according to their X-ray energies. The very faintest sources we're detecting in the centers of the Deep Field South correspond to about 1 count coming in every 10 days. Okay, which is, I find, quite impressive. If you can build an observatory that can detect 1 count every 10 days and a camera that can detect 1 count every 10 days, you think you did a pretty good job. Okay, so it really is a wonderful observatory that's made all this possible. Okay, so that's a little bit about the Chandra Deep Field, specifically the Chandra observations. I also want to mention that there's a lot of other exceptionally great complementary data. In the X-rays, NuStar has now done higher energy X-ray observations of the Chandra Deep Field-South. This is a work by Mullaney et al. They've detected a significant number of X-ray sources, as you can see, letting us home in on some of the very highly obscured systems. And furthermore, there's also a large investment of XMMNewton time led by Andrea Comastri and collaborators that let you do good additional X-ray spectroscopic studies of the brighter X-ray sources. There's a lot of wonderful additional X-ray data by other missions on this field as well. Now, I'm often asked and sort of prodded once in a while, why did you go so deep? Why did you need all this Chandra time? Well, there are 2 big reasons, to my mind, why I think it was worth doing. To begin with, one big thing is to detect new sources and new source classes. And in particular, by going this deep, we're aiming to find obscured, growing supermassive black holes through the full era of massive galaxy formation, to find the obscured systems that are otherwise hard to find and really be confident that we found all of them. And you really need to go super deep because even systems that are very luminous and are producing a lot of power corresponding to a lot of black hole growth can be very faint if the obscuration is very high. Furthermore, we're after growing supermassive black holes in the first galaxies. I'll tell you about some efforts to study those in a little bit. And we're also trying to learn, in addition to active galaxies, to learn about X-ray binary populations in cosmologically distant normal and starburst galaxies and how X-ray binary populations evolve. And I'll say a few words about that as time allows. In addition to that, however, you also have this additional major theme, and that's to understand the current sources, the ones you detect even with 1 million or 2 million seconds of data, much better. Just gathering enough photons to characterize these sources so you can fully utilize the spectral and timing capabilities of Chandra is another reason why you need these very long observations. And we've been doing a lot of work in that regard. And Chandra is extremely powerful for that, just because of its truly excellent PSF, which gives you, even for quite faint sources, very high signal to noise, and lets you perform reliable spectroscopic studies of even very faint sources. And I'll just show you a few examples very quickly. One, here's a nice study recently led by my student Guang Yang, where, of course, as I said, the observations span about 16 years, and so we see X-ray variability, and you can see their X-ray variability of these sources over the years. And we use that to characterize the AGNs better and to characterize the stability of our overall conclusions and whether they would change if you observe the field years later. We also, again, have variable X-ray spectra. You're seeing in the panels on the left there an example of luminosity variability, and in the panels on the right an example of X-ray spectral variability where the absorption along the line of sight is changing, perhaps due to the obscuring material rotating around the black hole. So that's one example of spectral studies. By getting the really good spectra, you can also perform via direct spectral fitting the best possible characterization of the column densities, the amount of obscuration present in these systems. And you can see many of the sources indeed have a very large column density of obscuration, 10 to the 23, 10 to the 24, and so on, as you can see there. And this is nice work that's ongoing by Teng Liu, where he's also using direct X-ray spectral fitting to set the best possible constraints on the luminosity and redshift dependence of X-ray obscuration. So there's a lot of good work to be done with that. Now, by going very deep like this, we are aiming to get this type of X-ray characterization for the sources that produce most of cosmic accretion power. That's the aim. Okay. And here's a plot that illustrates that. This is showing the Chandra Deep Field-South sources, and I'm plotting there in red the sources that have more than 500 full band counts. Okay. And so these are the sources where we have sufficient counts that we can actually characterize these sources fairly well. And you can see we have large numbers of counts for sources spanning a very wide range of redshift, okay, and spanning both above and below the break in the luminosity function. And you need to cover that range of the luminosity function to get the sources that produce most of cosmic accretion power. Shallower surveys, like, for example, Cosmos, which is a great survey, but which is about 44 times shallower, has 44 times fewer counts, and has trouble doing X-ray spectral characterization of these sources. So that's another unique aspect of the Chandra Deep Fields. Now, again, I want to say some words about the multi-wavelength data, which are absolutely essential. Here, of course, is the famous Hubble Ultra Deep Field that lives down in the center of the Chandra Deep Field-South. And there's a lot of wonderful additional Hubble imaging over the field via the GOODS project, which I was fortunate to be able to be involved with for many years, the CANDLES project, GEMS, and so on. So there's a lot of wonderful HST imaging. I'll show you some HST images in a little bit. And there's also wonderful spectroscopy, infrared data, both ground-based and space-based. Now ALMA is giving all sorts of great data on the Deep Field-South, letting us probe forming galaxies, and we can explore the black hole growth in forming galaxies, the VLA and the radio band, and so on. And all of these data sets are critically important for source identification, for classifying the nature of the sources, for measuring the properties of the host galaxies, and so on. And this multi-wavelength aspect continues to improve rapidly. I'll say more about that at the end. And this is what's kept the science exciting for so many years, in addition to, of course, the X-ray data getting better and better. So here are the detected source number counts presently for the Chandra Deep Field-South as derived by Brett Lemur. And you can see that the AGN number density has now reached very, very impressive values. We're getting about 23,900 AGNs per square degree in the Chandra Deep Field-South. And this is a representative patch of sky. If you scale it up to the entire sky, that corresponds to about 1 billion active galactic nuclei across the sky. That's what we're getting to now. And at our flux limits, we're about a factor of 20 higher in source density than the deepest optical AGN surveys, and that's because, again, we can find the obscured systems and the systems with a lot of host galaxy light dilution. And when we torture test our X-ray selection techniques versus other techniques, using all the multi-wavelength data, we find that the X-ray selection, while not perfect, holds up very well, particularly considering purity. When we say something is an AGN, we're indeed confident it is. Now, in addition, I'll also just say briefly that we are resolving, according to our best assessments, and we're still working on this further with the 7 megasecond data, something like 80 to 85% of the cosmic X-ray background, all the way up through about 8 keV. So we're getting a very large resolve fraction. Now, in addition to all the AGNs, as I alluded to very briefly earlier, we're also detecting a significant population now of cosmologically distant normal and starburst galaxies. And here we're detecting the X-ray binary populations collectively in these galaxies, and we can learn about how those X-ray binary populations have evolved. And at the very faintest fluxes, you can see the galaxies are in fact just overtaking the AGNs. Okay, here are our counterparts and redshifts. We now, via enormous work, by our team as well as by many other teams around the world, have something like 98.4% of the X-ray sources having counterparts. Also 97.8% of them having redshifts, with most of those being spectroscopic spectroscopic. And the remaining ones, the photometric ones, are very high quality, typically good to within a few percent because of the fact that we have so many multi-bands to constrain the photometric redshifts. In addition, this is our overall redshift distribution. You can see we are indeed sampling a wide range of cosmic redshift. And when we fine bin the redshifts, as you can see in the right-hand panel there, you can see the many spikes of cosmic structure running through the Chandra Deep Field-South as being traced by the AGNs. Okay, here are some nice plots just showing examples of the X-ray sources, and in this case, Hubble Space Telescope imaging. And so the circles there are showing the positional uncertainties, and the very small positional uncertainties are essential for reliable source identifications. And you can see we have very bright optical sources corresponding to AGNs, also very faint ones. There's a wide diversity there. And we can characterize all that, measure morphological properties of the host galaxies, measure stellar masses, measure star formation rates, and we're going to be using that later in the talk. Here are some more examples. Here are some more. I could look at these all day. They're so much fun. I have page after page of these things. I spend entire days doing this. Just kidding. But anyway, so now I want to get on to sort of the meat of the talk. This will be a little more in depth. I want to tell you about some selected first science results from the 7 megasecond Chandra Deep Field-South. And here, of course, I will just be skimming the surface, and I want to say that there are many other great survey results derived by our team, as well as many other teams around the world, constraining the demographics of the AGN population, constraining the physical properties operating in these systems, constraining how the black holes and the host galaxies interrelate, the so-called black hole ecology. And so if you want to learn a lot more about those things, we have with substantial effort written a large review paper that gives you many more details. So today I'm going to just hit some of the highlights, and I will suppress some of the complex details due to the limited time. So here's one example that we've been working on very recently from the 7 megasecond Chandra Deep Field-South. We're trying to learn, in this case, how the black hole accretion in the galaxy population in general depends on host galaxy star formation, host galaxy stellar mass and star formation rate. And this is work that's been led by Guang Yang, a very good student in my group, as well as Chin-Ting Chen and Fabio Vito and others. And I'll give you some context here. So for a while now, there have been these very interesting suggestions in the literature of a simple linear correlation between galaxy star formation rate and sample average black hole accretion rate. So you average over a sample, and you find a quite good relation between those two quantities. And you can see that in the two plots that I'm showing there for a low redshift bin and a high redshift bin. Look at the black data points there. Okay, people like Chen et al. Have established that this exists up at high star formation rates, and we wanted to extend this to lower masses and lower star formation rates using the Chandra Deep Fields. And so we took, in this case, about 18,200 galaxies with stellar masses and star formation rate measurements from candles, and we used the Chandra data to estimate the black hole accretion rate. And because of the great depth that we have in the Chandra Deep Fields, again, we can push to much lower stellar masses and star formation rates than many previous samples. And one notable thing that we noted, that we came across when we were doing this, is if you take the relation that I've been speaking of, the black data points, and you split them by stellar mass, you find a quite clear separation out depending upon stellar mass. And you can see that plotted there, such that at a given star formation rate, objects with higher stellar masses are clearly more likely to be hosting, accreting black hole accretion. Okay, and this is a pretty substantial splitting. It's like a DAX or so. And so it's pretty clear that star formation rate is not the only factor, and that stellar mass must be playing a large role. And so to investigate that further, we actually have been making plots like this, but flipping the variables, plotting the same quantity, black hole accretion rate versus stellar mass, and then splitting it by star formation rate. And we find much less of a splitting occurs there. And indeed, when we perform partial correlation analyses, our best assessments right now, the data are suggesting that the black hole accretion rate relation with the stellar mass may in fact be likely the primary one, and the black hole accretion rate star formation rate relation may largely be a secondary effect. It is there, but at a more secondary level, and that would be arising due to what's known as the star formation main sequence, the known correlation between stellar masses and star formation rates in galaxies. In addition, we've investigated the ratio of black hole to host galaxy growth as a function of galaxy stellar mass, and you can see that plotted there. And it's what we find quite clearly is that more massive galaxies have higher ratios of black hole growth rate to host galaxy growth rate, okay, than low mass galaxies do. And why is this? Well, we're thinking about that quite a bit. It may be due to the deeper potential wells of massive galaxies promoting supermassive black hole accretion and being more effective at countering feedback. And given these results, you would expect, for example, low mass galaxies to have undermassive supermassive black holes compared to the black hole stellar mass relations derived primarily from much more massive galaxies. Okay? And this is quite interesting given that there are now measurements in the local universe indeed finding suggestions of things like this. And so we may now be seeing the origin of that mass dependence out in the distant universe. And there's many other important implications there, but I'm not going to get too thick into it, and I'm going to just show you some other nice results. Another thing that's been done, and this is work by Mu-Yuan Sun and John Trump and others, is we've taken the massive individually X-ray detected systems and we've estimated supermassive black hole mass for them, using their emission line properties, and of course the black hole accretion rate. That's the derivative of the black hole mass, and that's what's being plotted there along the y-axis. And similarly, we've estimated the host galaxy stellar mass and its derivative, which is the star formation rate, along the x-axis. And you can see there that compared to the local relation, which is the shaded plot, out at redshifts, out to about 2 or so, we don't find any strong evidence for systematic evolution of the black hole mass, host stellar mass relation. And furthermore, when we do find outliers, their growth vectors are generally pointing back toward the relation. So we're actually able to trace the formation of that relation out into the distant universe. Now I want to talk about a technique known as stacking, which we use to push the X-ray data even harder than you can with the individual detection limits. And I want to explain stacking with this slide here. This is perhaps the favorite slide that any of my graduate students has ever made. I thought this was very clever. This is work by Brett Lemur. Brett, at the time he made the slide, I believe he was just about to propose to his girlfriend, and so I call it the romantic example of stacking. Okay, and you can see here, this is a nice, so what Brett did is he took a bunch of key candles and he stuck them on his stairs. Okay, and he took pictures of them, one with a 3 100-second exposure, shown there in the top, and one with a 1 1,000-second exposure down there in the bottom. Okay, and the idea then is that if you take all these low exposure observations and stack them up, you should be able to recover an effective image that has the exposure time of one of these. And indeed, if you look at that bottom panel, I can't tell how well it's showing there, but you can actually recover the flame very well. You can recover the candle wax very well. You can recover the candle's wick very well. So that's the idea of stacking. And we can use that exact technique, which of course is also used by cell phones to take low light images in many cases, as well as by amateur astronomers. We can use that same basic technique to study the distant galaxies and active galaxies in the distant universe. And here's an example. So here, this is again work led by Brett Lemur, where he's taken the 7 megasecond data and he's stacked up non-active galaxies in the deep field south. And here, these are systems where, again, the primary X-ray emission is dominated by X-ray binaries. And he's been able to perform the best characterization of X-ray binary populations as functions of star formation rate and stellar mass, as well as redshift, out to quite high redshifts, out to redshifts of about 2. And these results pin down the most likely population synthesis models that people have put forward for X-ray binary populations. And furthermore, he finds this quite notable dependence of X-ray binary emissivity in the X-ray band per unit star formation rate with redshift. And you can see that there, this rise in that quantity with redshift. And that's indicated that the X-ray binary populations are becoming more effective per unit star formation rate at generating X-rays as you go to high redshift, quite possibly associated with the lower metallicities of the higher redshift galaxies, which promotes the amount of X-ray binaries per unit star formation rate. Okay, you can also use stacking to investigate very high redshift systems. In this case, we're trying to get at the seeds of the first supermassive black holes in the universe. So here we're using stacking to push absolutely as faint as possible to try to to learn what we can about black hole seeds. This is clearly very demanding work. This is also work that will ultimately, hopefully, be pursued by the Links mission, but we're doing our best to explore this parameter space now so that we can learn as much as possible to guide the development of missions like Links. And so what we've done here, and this is work that's been led by Fabio Vito, is we've done X-ray stacking of individually undetected galaxies, so none of them are detected, and we stack them all up, and there's large numbers of high redshift galaxies that have been found in the Chandra Deep Fields, and we have between about 100 up to about 1,400 per bin. And even though these galaxies are individually undetected, we can pull up average X-ray detections, as you can see there along the top panel. Oops, those are for all the galaxies in our sample, the top panels. And at the bottom panels, those are for just the most massive half of the galaxies, where in fact we find that most of the X-ray flux comes from the most massive half of the galaxies. Okay, so we can pull up these X-ray detections, and we can then go and, using the characterization I've just described back here of how X-ray binary populations behave with redshift, we can look to see the origin of this X-ray signal, and we find it is quite likely associated, all the X-ray emissivity that we're seeing here is in fact likely from the high mass X-ray binary populations in these galaxies. We again can characterize these galaxies well enough to be able to predict what their X-ray signal should be, and we find that the X-ray flux is consistent with that. So there doesn't appear to be much signal at all among the individually undetected population for any further supermassive black hole growth. And so the basic constraint here, okay, is that most high redshift supermassive black hole accretion occurs in a short AGN phase, and that any further growth, any sort of continuous low rate accretion contribution out of very high redshifts has to be quite small. Now, we hope to push this even further in the future, especially when the James Webb Space Telescope comes along. We've already pushed our stacking results out to even higher redshifts. As you can see from this table, we've been pushing them even out to redshifts of 8. We don't get detections right now because the observations aren't all that long when you stack them, where again I want to point out that back here when you stack up all these observations, in this case here we have about 1,400 galaxies, you stack them all up and you have an effective 8.2 gigasecond Chandra exposure, okay? So that's like a 265-year Chandra exposure. So if you pointed Chandra at this field for 265 years, something that I'm personally in favor of, then you would detect these galaxies. Okay, so anyway, that's one thing. Now, of course, we can do much better in the future. The problem with the very high redshifts now is not necessarily the Chandra data. It's actually the lack of more galaxies to stack. But when James Webb Space Telescope comes along and provides large samples of very high redshift galaxies with better redshift identifications and better removal of low redshift interlopers, we aim to push these Chandra stacking analyses out to redshifts of 10 to 15 to place the best possible constraints upon the first seeds that formed the supermassive black holes that we observe at lower redshifts. And one could also envision stacking 21 centimeter selected regions or doing cross correlations between 21 centimeter measurements and X-ray measurements, and there's a lot of exciting possibilities there. I think I will end with this section by just also mentioning one other very interesting object. So one day, Bin Luo, a student in my group, was analyzing the latest Chandra data set that had come in, and he came to me and said, well, there's this new bright X-ray source in the field, and you know, this can't be because we have millions of seconds of Chandra data before and there's absolutely nothing there. And of course, we went and checked very carefully that it wasn't some kind of instrumental systematic. The Chandra X-ray Center helped us make sure that wasn't the case. And indeed, we believe we found a new type of X-ray transient that we just stumbled across fortuitously because we were exploring this new part of parameter space, you know, the very deep, very sensitive transient universe. And in this case, you can see the source. We have about 115 counts from the source, so we can't do detailed spectral characterization, but we do have basic X-ray spectral characterization, as you can see in the lower panel. And Franz Bauer took over the work because we were too busy trying to get all the Chandra data processed and get all the cataloging done, and he did a really great job investigating this object. We do find a counterpart for it. It has an extended optical counterpart you can see there that's very faint. It's down at sort of 27.5 magnitude. Its photometric redshift is not very well constrained as a result of that faintness, but it has to be a dwarf galaxy. This is some little tiny dwarf galaxy out in the very distant universe, okay? And we're seeing some type of new transient transient behavior from it. And by chance, just because the Chandra Deep Field is so extensively studied, there's no optical transient that we're able to detect. And in fact, by chance, we didn't try to do this, someone obtained an optical image, a deep optical image, 80 minutes after the X-ray transient, and there's nothing there. And in multiple additional follow-up observations that Franz and others have led, there's no additional transient seen there either. Now, to compare this transient to other known source populations, Franz compiled this nice diagram. It shows the swift gamma ray bursts along there. Those are where typical gamma ray bursts are. Oops. And this particular transient is shown there in the red for the two possible redshifts, and the intermediate values, of course, lie intermediate. And in addition, a number of other types of transients are also compared, and all the transient lovers will know all those things by heart, so I won't explain them. And the basic result that we're finding is that the X-ray luminosity is much lower than that of typical gamma ray bursts. And furthermore, the optical limits lie significantly below the expectations for a typical gamma ray burst afterglow. So perhaps this is an off-axis gamma ray burst. That's something that's been considered. It could also perhaps be the beam tidal disruption of a white dwarf by an intermediate mass black hole, and some people are also suggesting it could be a millisecond magnetar. We don't know what it is right now, but this is an entirely new transient class, perhaps analogous to these fast radio bursts that people are so excited about right now that we can hopefully go and explore in the future. And when we make basic assessments of the event rates for these things, they're estimated to be, their event rate is estimated broadly. Clearly, we only have one event, so there's a large uncertainty, but perhaps is broadly comparable to that of gamma ray bursts. Okay? So this is a new fainter X-ray transient class that will be great to explore with future X-ray missions. The proposed STAR-X mission would be one great way to do that, give you a much larger grasp to find more of these systems, as well as the Einstein probe being developed in China might be another good way to do this. Okay, now I'd like to end the talk by just reviewing some future prospects for X-ray surveys of active galactic nuclei. And I think there are really great prospects here still. To begin with, I want to stress that both Chandra and XMMNewton are still healthy. They're both doing great, and we can hope for them to last both until 2025 and beyond. Okay, so this would be my entire career, which should be great in some ways. So, and this plot here is in fact showing the state of health of all the major Chandra subsystems, and basically anything that was truly dangerous to the mission would be colored red, and there's no red in the diagram, which is a very good thing, and let's hope it stays that way. Okay, and so we can hope for another 10 years of X-ray surveys with these missions. Furthermore, in addition to conducting these targeted surveys, by allowing these things to continue operating, you're building up these wonderful archival databases, which are going to be extremely powerful when things like LSST and PFS and Euclid and WFIRST come on in full steam. The archives of these missions will be truly amazing when you can go and mine them fully with all that multi-wavelength data in hand. I also want to stress that for the deep surveys, there's again a lot of great new complementary multi-wavelength data that continue to flood in. Here are some examples from the Chandra Deep Fields. Of course, the EVLA and the next generation VLA will be great for studying these things. The James Webb Space Telescope I've already mentioned. LSST will be fantastic. LSST will be doing deep drilling on the Chandra Deep Field-South, which is one of its pre-selected deep drilling fields, and that will be very exciting to do extensive variability studies. In addition, ALMA is just ramping up still and is already doing all sorts of great stuff on the Deep Field-South. Better spectroscopy is very important as well. I now want to end by talking about some future X-ray missions. First of all, I'll just mention Rosita. Rosita is launching soon. It's an extremely exciting mission. It will do a much better generation of all sky surveys than we've had currently. Here is the sort of schematic for where Rosita lies in this plot of flux limit versus solid angle. It will be about 20 times more sensitive than the current all sky survey in the soft X-ray band, and much more sensitive still in the high X-ray band. And it will discover about 3 million AGN. So there'll be plenty of AGNs to go around for everybody at that point. You will all be completely overwhelmed. Okay. Furthermore, the Chandra Deep Fields are great, but one problem is there's only 2 of them. I'd like there to be 100. Okay? Clearly, no one's going to let me do 100 with Chandra, and so one will have to move to new facilities to be able to do that. And the Athena mission, it will be wonderful when it begins operation for probing that part of parameter space, generating large solid angles with near Chandra Deep Field depths. Okay, it won't quite match the Chandra Deep Fields, but it'll be pretty darn close. And so that will, of course, let you do a much better exploration of, for example, high redshift AGM populations, where the source statistics are pretty thin due to the small solid angle of the Chandra Deep Fields. It will also let you do wonderful studies of the environmental dependence of supermassive black hole growth, ranging all the way from the voids to the most massive superclusters in the universe, and so on. And of course, it will also give you much better photon statistics for characterization. Now, in addition to Athena, there's also, again, as I had mentioned previously, a very exciting proposed mission called StarX, which will, in addition to doing all sorts of amazing transient work as an additional benefit, will also cover that part of parameter space. So that would be very exciting if that happens as well. And then, of course, it's also very important to advance the hard X-ray surveys. People who came up with NuSTAR are trying to develop a probe mission concept called HEXP that would achieve about 40 times the sensitivity of NuSTAR in the 10 to 80 keV band, and of course we'll go to even higher energy still. Here are some of its characteristics. It would be so powerful because it would have better imaging than NuSTAR, as well as a larger photon collecting area. And this would be able to resolve about 90% of the cosmic X-ray background up at its 20 to 40 keV peak, which still is a very important thing to do, finding many more examples of obscured AGNs and many Compton thick systems and so on. And then in the very distant future, we can dream about missions that would achieve sensitivities far beyond those of Chandra. In particular, there is this mission concept currently being developed called Links. This is an ongoing NASA mission study, and here are some of the people who are dreaming about Links right now, and it would be truly wonderful if it happens. It would be able to probe to much greater depths than the Chandra Deep Fields, because it would maintain Chandra-like imaging, okay? But do it with a vastly larger photon collecting area, let you going down to much fainter flux limits. And that would be capable, truly, of probing the seeds of the first supermassive black holes. At a redshift of 10, you could get down to sort of 50,000 solar mass black holes, or perhaps even somewhat smaller than that, including obscured systems. And you would hope to be able to discriminate the sort of low mass population 3 remnants from these direct collapse black holes using measurements of the luminosity function as well as measurements of the host galaxies of these objects. So I'll wrap up there, and thank you very much. Okay.
So we have time for some questions. If you'd like to ask a question, could you come up to one of the microphones that are in the aisles? I think there's a microphone on this side, and there's a microphone over on the other side as well.
Yes.
Just curious if you could comment on the potential for spectral line stacking in the X-ray.
Yeah. Yes. Spectral line stacking in the X-ray is done and will continue to be done in the future. I mean, that becomes more and more possible once you have precise redshifts for large numbers of these systems. But certainly, people have taken large numbers of active galaxies and stacked them up to measure, for example, the equivalent width or the profile of the iron K line, and in some cases there are claims that you see broad iron K lines from the relativistic part of the inner accretion disk, similar to what's been found in many local AGNs. So yeah, there's certainly a lot of work in that, and it's a very good thing to be doing. And I can give you some references on that type of work at the end if you're interested. Okay. Yeah.
Well, thanks. So if there aren't any more questions, let's thank Niel once more for such a fabulous, exciting talk.